Let us move on then and look at the details of an anchor example. This is a rather simple case, but it's been designed for illustrative purposes only. We will have two anchors in this example, but once again it's been designed to illustrate techniques as opposed to a realistic field case. So in this anchor example, we will have an anchor spacing along the wall where the spacing of the anchors is 2 meters. Slope W is formulated for analyzing a soil slice 1 meter into the paper. And so when we have things like anchors, we have to, number one, normalize the anchor such that it is analyzed per meter into the paper. We're going to start with a bond length. The total length of the anchor will be 6 meters. And we're going to start with an option which says that I am going to apply 600 kilonewtons from the anchor, and the purpose of this is to see and do some analyses where the load stays constant regardless of the position of the trial slip surface. The bond length is going to be 3 meters. And notice here that we have accepted a diameter which is 1 over pi, which is a default diameter such that we can talk about kilonewtons per meter. And the bond skin friction will be 300 kilonewtons per meter squared, or 300 kilonewtons per meter. We will have a factor of safety on the pullout of 1.5. The bar capacity will be 2,000 kilonewtons, and we will apply a factor of safety on the 2 on the bar capacity. Let us go then to GeoStudio and open up SLP 21. Sorry, this should be SLP 23. And we're going to begin by asking the question, what force do I need out of my anchors in order to get a design factor of safety of 1.25? When you open up SLP 23 and you click on the GeoStudio icon here, the start page, you will notice that there are 5 different analyses in this file. We're going to start with the first analysis called constant load. Once again, if you zoom in on the All Objects zoom button, we don't need the snap to grid because the problem has already been defined. But we need to look in detail at exactly what we have defined here. There are actually 2 ways of doing this. One way is we can zoom in on the anchors and we can say draw reinforcement loads. And notice that when your cursor turns to an arrow, you can select a predefined anchor. You have to be very careful in this mode. When it's a plus sign, you will draw a new anchor, but it has to be an arrow, and then you can select the anchor. Another way to look at the same data is with key in reinforcement loads. And here both anchors are listed. We can select either one The advantage of the key-in reinforcement dialog box is that we can select multiple anchors and change parameters on those anchors all at the same time. I will try and illustrate this a little later on. Let's go back to draw reinforcement loads. And we need to draw your attention to several things. First of all, I need to select an anchor. I will select the top anchor. Notice that I have selected anchor as the type here, and its factor of safety dependent no. The load is concentrated in one slice. We said that the length was 6 meters and the direction is 21.8 degrees. Now in this case I have selected this option here that says constant applied load. What this means is that the anchor load will be applied as a certain value regardless of the position of the trowel slip surface. It's a useful option to try and answer the question, what do I need out of my reinforcement to get a particular factor of safety? If we use the variable load, which we will do in just a minute, then the anchor load is dependent on the position of the trowel slip surface relative to the bond length. So to start with, we are going to start with the option constant applied load. We have specified a constant load of 600 kilonewtons. Sorry, we'll go back to draw reinforcement load and select the top anchor. And we have selected 600 kilonewtons. So at this stage, we need to take the 600 kilonewtons and divide by the spacing. So it's 600 divided by 2 is equal to 300 kilonewtons. The bar capacity is going to be higher than this value, but we'll come back to that in a little bit. Notice that the applied load here is 300 kilonewtons. We have a bond resistance here of 100 kPa or 100 kilonewtons per meter. This will be used to show the length of bond required, but will not be used at this stage in the factor of safety calculations. We're going to come back to this in just a bit. We can click on the lower anchor and see that the definition is the same as the top anchor. We now can click on the Solve button, and perhaps it was already solved, but let us resolve the problem and go to the results view. I will turn off the shading of the potential sliding mass, keep up my slice discretization. The important point here is that number one, we have used 300 kilonewtons for each of these anchors. We can verify this with view slice information, and once again, as we have done in the past, when we look at the various slices, we see that the slice where the anchor intersects the base of the slice has the 300 kilonewtons. Here is the 300 kilonewtons. So it's the 300 kilonewtons that has been used in the force resolution on this slice to compute the factor of safety. The same is true for the lower anchor. Once again, we have the 300 kilonewtons. So the factor of safety that we have computed in this particular case here results in a factor of safety of 1.25. Now, stated another way, what this is saying to us is that in order to get a factor of safety of 1.25, I need 300 kilonewtons out of each of these anchors. Or in other words, 600 kilonewtons if we take away the spacing. I will turn off my safety map here to look at this in a little bit more detail. And what I want to draw your attention to here is that we have used 300. We had 100 kilonewtons per meter. In order to supply the 300, we need a bond length of 3 meters. And so in this particular case, we have drawn a red box that illustrates the size of the bond that is required to supply the 300 kilonewtons. And we notice that the available bond is not sufficient to supply the 300 kilonewtons. The reason we were able to do this is because we had selected the constant option. So, at this stage we know that we need 300 kilonewtons per meter into the paper from each of these anchors to give us the desired 1.2 factor of safety. So let us go back to the defined view and look at lengthening the anchor. We can now go to analysis number 2 and notice that the anchor already has been lengthened. The way this was done is draw reinforcement loads. We click on the top anchor, again once it's an arrow, and initially this was 6 meters here. This is where we were at. All that was done in this particular case was to enter a length of 8 meters for the anchor. Notice that the bond length stays the same, and immediately the cross-section is updated to represent the 8-meter length of anchor. Now when we reanalyze this case, the second analysis, and look at the results view, we notice that the factor of safety is identical, but in this particular case the required 3 meters of bond is in front of the available 3 meters of bond. So in this particular case, the red box shows that the anchor is long enough and that we would actually be able to mobilize 300 kilonewtons out of the available bond. Now let us go back to the define view and look at analysis number 3. And we are now going to switch over to the variable load option, draw reinforcement load. Clicking on the top anchor, we now see that we have switched over to the variable applied load. Notice also the applied load is now arranged down here, and it's worth spending a few moments as to what this means. Once again, what is available to us is 3 meters of bond length. The bond skin friction is 300. And we multiply it times pi divided by 1 over pi meters, gives us 300 kilonewtons per meter. We have to take the 300 kilonewtons per meter and divide it by the spacing of 2 meters, gives us 150 kilonewtons per meter into the paper per meter of bond. Then we have to take the 150 kilonewtons and divide it by a factor of safety equal to 150 divided by 1.5 gives us 100 kilonewtons per meter of bond per meter into the paper. So depending on where the slip surface is located, what we could get out of the before we do that, we have 100 times an available 3 meters, so the maximum bond we can get is 300 kilonewtons. Now, depending on where the trowel slip surface is, the available pull-out is between 0 and 300 kilonewtons. If this is the bond length here and the slip surface goes behind the bond length, then the anchor simply goes for a ride and we get 0. If the slip surface is in front of the bond, the maximum we can get out of the bond is 300, so the applied load could be anywhere between 0 and 300 kilonewtons. Let's talk a little bit about the bar capacity. The bar capacity is 2,000 kilonewtons. So again, 2,000 kilonewtons divided by a spacing of 2 gives us 1,000 kilonewtons per meter into the paper. We take the 1,000 kilonewtons and divide it by a factor of safety of 2, means we get 500 kilonewtons per meter into the paper out of the bar. The bar has a higher capacity than the bond. Therefore, the bond governs. In this particular case. In other words, we will have pull-out before we break the bond. We will have pull-out before we break the capacity of the bar. Let's go now and look at the results. In this particular case, it turns out that the variable option results in exactly the same factor of safety because the critical slip surface is in front of the bond and the bond is able to supply the 300 kilonewtons that we intended in order to get a factor of safety of 1.25. Let's once again zoom in here, and we can now look at the results in a different way. We can say we are in the results view. We go View, Object Information. And if we click on the anchor, we have a large amount of information here about the anchor. Once again, notice that we have used the 300 kilonewtons. The available bond to supply the resistance was 100 kilonewtons per meter, We have an available bond of 3 meters. The required is 3 meters. Therefore, the governing component is the bond. We can look at the same information for the lower anchor, and once again it is exactly the same. So in this particular case, all else being the same, the variable option gives the same result as the constant option, which is usually the ultimate objective. Now I want to draw your attention to another issue, and that is the normal stress distribution along the trowel slip surface. We say draw a graph, we add a new graph, and we're going to plot the normal, the base normal versus slice number. And notice now how the normal becomes very high for the slices that have the anchor force included in the force resolution of those slices. Also of great significance is if we say view slice information and we start looking at slices that are above the top anchor, and we watch the free body diagram and the direction of the forces, notice that there is no effect on this slice from the anchor, but when I get my 300 kilonewtons added, notice that what happens to the force here. It starts to point away from the slice. Now, the immediate reaction is that this infers tension between the slices. Actually, this is not what it actually does, although there is an urgency to think that that is what we are in actual fact doing. So now in this particular slice here, we notice that the force points away from the edges of the slices. We can look at this another way by saying draw a graph, and let's add another graph, say interslice. And we look at interslice data, and we want to look at the interslice shear forces, the interslice normals versus slice number. And notice now how that the interslice normal is positive, but then goes negative for a ways, becomes positive, and again goes negative. This is one of the consequences of concentrating all of the load in one slice, and it produces this unrealistic stress distribution along the slip surface, and it produces the unrealistic interslice forces. Now, fortunately, as we will see in a minute, it does not affect the factor of safety all that much, but it is something that you should be aware of and know how to handle. Let us go back then to the define mode and go back to the next analysis, evenly distributed. So now instead of concentrating the load all in one slice, we will distribute the anchor load amongst many slices. Let's say key in reinforcement loads, and we notice in the top anchor we have now said that the force will be evenly distributed, even along the reinforcement. I'll show you in just a few moments how this works. What I want to point out to you, if you hold down the control key, that we can select we can select this option here and change both anchors at the same time. So in this particular case, if I now select one, notice that they have both been changed. So the key in reinforcement dialog is sometimes useful for this purpose, and so we want to change both of them to even along the reinforcement. We can reanalyze the result and go to the results view. Let's go back to analysis number 3, and where we had it all concentrated in one slice. Now the factor of safety is 1.257. If we evenly distribute the load amongst many slices, the factor of safety is almost the same, 1.27 versus 1.26. For practical purposes, it is essentially all the same. Now, first of all, the effect of this is that we get a much more realistic stress distribution. If we say graph interslice forces, you notice that all of the negatives between the slices has now been removed. And also, this was our normal stress graph. And we also notice that the base normal does not have these peaks now. It is more evenly distributed. So this is much more realistic. But once again, notice that it did not have a great deal of effect on the overall factor of safety. Now, one thing I need to draw your attention to now, if we go View, Slice Information, and we click on the slice that encounters the anchor, notice now that the force is only 16.66. It was initially 300. The 300 is divided amongst a group of slices. And in this particular case, the 300 is divided amongst, I think it is 18 slices. 1, 2, 3, 4, 5. I think if you count them up, you will get 18 slices here. So if we take the 300 kilonewtons and divide by 18, then we get a force of 16.66, which we saw is what slope W had used. In other words, the 300 is divided amongst all of the slices that are intersected by the top anchor. Now, if we say View Slice Information and we keep on going, we see that each of these slices has 16.67 until we reach the lower anchor, and all of a sudden we have a much higher number. Now remember, this is the slice, and in this case here we have a value of 54.167. In this particular case, we took the 300 and divided it by 1, 2, 3, 4, 5, 6, 7, 8 slices. So in this particular case, we have (300) divided by 8 is approximately 37.5, and the 37.5 plus the 16.67 from the top anchor gives us the 50. So 300 divided 8 plus 16.6 gives us 54.1, and that is what we saw Slope W had used. Once again, view, slice information. You notice that here is the 54.1. So this becomes a little bit more difficult to interpret as to the exact total that has been used by each one of these anchors. If we go to, in the results view object, and we click on the anchor, then once again here you can see the total. In the slice information we don't see the total. Here once again you can see and verify that it has used the total 300. Initially, when we started with Slope W, we always concentrated all of the load in one slice, and while that gave an acceptable factor of safety, we later added the evenly distributed option, which gives a very similar factor of safety in most cases, but it does produce a more realistic picture of the stress distribution along the sliding surface or the interslice forces, and so we are more and more in favor and wanting to use the evenly distributed option. Now I want to draw your attention to one other feature with anchors, and that is that there are those who believe that the anchor offers some additional resistance to sliding due to the shear, and you can accommodate the shear in the anchor. And if we go back to the define view and select analysis number 5, and then we say draw reinforcement load, and we click on the bottom anchor. I've added shear here only to the bottom anchor. Notice that I've added a shear here of 50 kilonewtons. The shear can be applied parallel to the slip, or you will see if you click on this down arrow that the other option is to make the shear perpendicular to the line of action of the anchor. In this particular case, I have just left it as being parallel to the slip. So just for illustrative purposes, I've left the shear factor of safety as 1. If we go to the results view and we go view, slice information, and we look at the slice that encompasses the lower anchor, we now see that we have the anchor force here of 300, but we have this additional shear of 25. 50 divided by the spacing of 2 is 25. So here's another feature that you can use if you are comfortable relying on shear in the anchor. But remember, once again, it has to be per meter into the paper, so to speak. There is one more issue I want to draw your attention to, and that if we look at our safety map, we see we have a very wide red band saying draw safety map. All of the slip surfaces that fall within this red band are between 1.35 and 1.45. So that means that there is a large zone where there are potential slip surfaces, and while the range here from 1.35 to 1.45 is quite large, it does point out the fact that there are multiple potential modes of failure that have similar factors of safety. And this is one of the issues that you will encounter with reinforcement. We will come back to this when we look at nails and geofabrics. But you always need to be cognizant of the fact that there is no one particular slip surface that necessarily totally governs. It's not too bad in this anchor example, but it does already lead you to the thought that there might be many modes of failure that have very, very similar factors of safety. So this is something you should always check and be aware of. Don't just rely on the one factor of safety for the slip surface that gives you the lowest value. It's useful to look at more than just that one factor of safety. This brings us to the end of the anchor example. There have been many features and methods illustrated here, and it takes a little while to get used to how to specify all these values. But in general, we recommend that when you use anchors, that you start with the constant option and try to answer the question, what do I need out of my reinforcement to get an acceptable factor of safety? And in practice, once you know that, you could then dimension the size of the anchor and select the materials for the anchor. And once you have done that, you can adjust the dimensions and the design if necessary. And in the end, we recommend that you always check the analysis with the variable option. Ideally, we should get the same as the constant. And our final suggestion is that you always watch for multiple modes of failure, and that you need to look at more than just the factor of safety. This brings us to the end of the anchor example.